Welcome everyone to TD Workshop 2. TD Workshop 2 means that we are halfway through with our semester. I know it's been tough. Online school, I have no idea how people do online education, but that was a killing zone, literally. I can feel you. But good news that we are, in 4 weeks, we'll enter our fall break. Yahoo! And we'll have Thanksgiving, so get some good food, not that bad food if you're not cooking, and reunite with family. I hope everyone is safe and healthy. So, workshop 2, we will be learning about machine learning. This is a very demanding knowledge in the field, and big companies like Google, Microsoft, Facebook already implemented it, but they are still improving that. They are improving that every day or every second. It's keep improving. This is new. This is helps the companies. And I would say not that big companies like Google they still implementing it right now. And I would say that in your job that you might have a project or your boss or employer will ask you to implement one in your company. And the good news is that when you complete this workshop, you'll be like, I can do that. So, in this workshop, we'll learn about handwriting recognition with neural network. It's a little bit complex, but I did my best to bring it down to beginner's level. I think this will be very beneficial in your interviews if you're interested in something like software engineering. What is machine learning? Machine learning involves a computer to recognize patterns by examples rather than programming it with a specific rules. These patterns are found within data. Machine learning is about creating algorithms, a set of rules, let's say that learns from a complex functions or patterns from data to make predictions on it. So, short, we take some data, we dump it in our machine. Machine finds patterns, learn from it, and makes predictions. And the bigger data set we have, the better prediction will be. So these are 3 training packages that you will be using when you will be creating machine learning. Number 1 is TensorFlow. TensorFlow is the base package and it's must use. It has all the functions that you need to create machine learning. The second one is scikit-learn. It is in addition to TensorFlow, and that's best suitable if you're dealing with a lot of numbers and statistics. And third one is Keras. Keras makes the process of creation machine learning much easier. It has already predefined functions and all you have to do is use them. It is best suitable for people who don't need complex machine learning or who are beginners. But if your machine learning is very complex or you have specific needs, Keras might not be that suitable. So before I dive into talking about neural network anatomy, I need to cover how our brain works because the whole process is the same with neural network. So the information comes into our brain and this neuron, the orange cell, will pick it up, it will get excited, and then it will need to send out that information to the next neuron. So the way it does, it gets excited and it creates an electrical signal, which will transfer the information to the next neuron. And this is a machine learning algorithm made up of individual neurons, and each neuron is responsible for performing a calculation. So the data comes into neuron, and the neuron makes the calculation and sends out to the next one. When we group them together, we will call them a layer. So we have input layer, hidden layer, and output layer. The data would come in, that's where we feed the data, and it goes through a neural network and our model will give us a prediction. A layer in between input and output called hidden neurons, and they make calculation and classification more accurate. But there has to be an optimal level because the more you have, the longer it takes for a model to learn and make prediction. This is actual neural network anatomy. But let me first talk about more easily. So it will take, let's say that these 3 neurons will send the information to this one. Let me grab the pen. And as each information is being sent to this one layer, oh, this is horrible. Let's do this. This one will have weight, this one will have weight, and this one will have weight. And these weights are the same. And they'll send the information X. And this one will send information X, and this one will send information X. And what this will do, this neuron, it will take this weight, so it will do weight of the first neuron, and then information of first neuron, it will add the weight of the second neuron. This is horrible. Okay, I'm doing my best. And then it will add from the third one. Almost there. There we go. All right, let me go to the next one. So this is basically what happens. It will take the weight of each neuron coming in, and it will sum them up, and also it will add some biases that could happen in our data. And then once the output is ready, it will send it to activation function. And activation function will decide whether this input is good enough to send out and activate the next neuron. So to sum it up a little bit, so we'll take the data, and the neuron takes the data, and then it will make it bigger by multiplying the weight. It will add some biases, and it will send it to activation function. And activation function then will send the data and activate the next neuron. So what type of activation functions we have? The first one we have is linear function. And this is the most basic and simple activation function. When we want to split up the data between two groups, right here we have orange and then blues, linear function is the best fit because it will put the line between them and it will just cut them in half. But if we have more than two groups of data, we would need nonlinear function because if we have, say, group here and group here, there's no way we could put a single line to split them up. And the next one, we have sigmoid function. And it's best fit if you have probabilities because the activation exists between 0 and 1. But as our x gets closer to 1 or 0, our model can refuse to learn anymore, or prediction can take longer and less accurate. And I'll show you an example later. Tan or hyperbolic tangent function activation is just an upgrade for the previous one. It has wider range from -1 to +1, and we can split up the data more accurately. And unfortunately, this function has the same downsides as the previous one, because as you can see here, it's like flat. So as it approaches 1, it will take forever to split it up. Rectified linear unit, or ReLU, is the newest activation function, and it is widely used. So if my x is -5, the function will return me 0. And if it's above 5, for example, if it's like 5, it will return 5. Next, I'll talk about learning rate and optimizers. We've seen this formula, and say I have neuron here, neuron here, and neuron here. They all calculate their own result and send to the new neuron. Since new neuron accepts them equally, that means that weight of each neuron is equal. Our goal for the model is to predict as accurately as possible. Or in other words, we need to minimize loss, or we need to minimize a wrong result. So say that this neuron gave the wrong result, some of the wrong results. That will make our model less accurate because it increases the loss. So how can we fix that? That's where optimizer kicks in. It will play with the weight of each neuron output, and it will see if by, say, decreasing this neuron, it will improve our accuracy. The optimizer doesn't know which neuron gave the wrong result. What it can do is just increase or reduce some of the neurons and see if that improves our model. So say our optimizer reduced the weight of the second neuron and it understood that this is the one that we want to reduce. That caused our loss to go down. But we need to tell optimizer by how much it needs to reduce the weight. Because every time it will reduce the weight, it will reduce the loss. And we want to take little steps because that's the level where we want to be. We want to have as minimal loss as possible. That's where learning rate kicks in. Learning rate will tell optimizer by how much it has to decrease the weight of the second neuron. Learning rate is basically a step down or up when optimizer is decreasing or increases the weight of each neuron output. We want to have learning rate very, very little, but not too little. By default is 0.01. And that means that it will take little steps to get to the level where we want to be. But if the learning rate is too big, say equals 1, and our starting point here, it reduced the weight of the second neuron by 1, and it actually ended up to be here. But we want to be here. So that means that by taking a huge step, we actually missed the point, our optimal point of loss. And when optimizer ended up to be here, it assumed, it was like, oh, so this is the minimum loss point, which is wrong. That's why you want to have a good optimal level of learning rate. The smaller learning rate is good, but it might take longer time for optimizer to finish its step. All right, let's dive into the playground, and this is the playground because it is playground.tensorflow.org. And this is a simulation where we can visualize how our neural network learns and how accuracy is being improved and speed by setting up specific configuration. So if you're interested in machine learning, I highly suggest going here and just play around. So we have here learning rate. By default is 0.01. I can significantly decrease the number, and it will increase the accuracy, but it will significantly decrease the speed, and I can increase the number, which will be reverse of that. I have activation. Remember those terrifying graphs I showed you? Well, here they are. We have linear, sigmoid, tan, and ReLU, and we'll look at them, how they work, and how they will classify our data. And last thing that I didn't mention in PowerPoint, that this is epoch. This is number of times entire training data is passed to the neural network for training. So let's take two data groups for now. And we'll start with linear. And linear will just place this white line in between two data and will classify it. I know it will not have any problems doing that. Let's do that. And I'll stop. It took roughly like 40 epochs or 40 times the training data passed to the linear activation, and it had no problem classifying two data sets dividing blues from orange. Our training loss is 0.002, which is amazing. That tells me that data is super accurate. I can do with each one of them, and as you can see, Sigmoid did a little bit better. It took really fast to classify two data. And then let's do 10. I'll stop right away. Also 42. And value. I'll stop also. No problems. Now let's take 4 data groups. And that's where linear regression will fail, because it is impossible to place a single line to split the data between 2 groups, even when us humans can. I mean, we can't put a single line, but we can split up the group more easily. For our brain, it will be so much harder to do that. So that's where nonlinear activation kicks in, which is ReLU 10 and sigmoid. So let's start with sigmoid. I will stop doing linear. I can show you that it will fail. It has no idea what is happening. And I'll do sigmoid. So from now on, I will not be doing linear activation anymore. So I'll start with sigmoid, and it failed. I'll explain you why. 10 failed, and value, it will also fail. So what happened? That's a signal that we need one more layer, which more neurons to pass the data and calculate the output. Think of hidden layer as additional people in your team. When you have a complex problem, but you don't have that many people in your team, the efficiency of your project will be worse. So hidden layer is a additional people in your team to which you can split up your project work, and the result of those people can be combined together. Let's add that. As you can see, something new happened. And if I'll start with sigmoid and I'll run that, it's taking its time, but it's taking too long, but that's a downside of sigmoid, as we have a lot of data that is close to -1 and 1, and it's taken such a long time to classify it. That's a downside. There we go, it's close. Alright, I'm gonna stop that. It took roughly 500 times to pass the dataset, and we have some losses here to classify it, and training loss is 0.184. Let's do 10. And 10 taken a little bit faster, I would say, but it failed. I can start again, and let's try now. Okay, it's doing something, but as you can see, every time I would start, something new happens, but it's failing. You can see that white space, it's failing. And for ReLU, it did good, better job than 10, but it failed here. So it tells me that I don't have enough people in my team, and I need to add 2 more people. As you can see, it already did something new. Let's start over, and I'll start with sigmoid. And it's taking a very long time. It's coming. There we go. It's already understanding. Splitting up blues from orange. Okay. Alright, so it will narrow down a little bit, but I'll stop it here. We have loss here. The orange do not belong to blues. You can see our training loss is 0.125. And then let me do 10. Okay, much faster. It's like Need for Speed. Meow. Cool. And as you can see that it took 4 times faster to classify our data, and training losses was much smaller, and it is performed better than sigmoid. And that's because our 10 function has wider space to place our data points and classify them. It's more accurate because it's not from 0 to 1, it's more of like -1 to 1. And our last candidate is ReLU. Let's look at that. Wow. Okay, it took much faster to classify it. Training loss much smaller, and as you can see, ReLU performed so much better. It classified, but if I continue, it will start narrowing down more, because as longer it takes time, our loss minimizes. And here's orange belonging to orange, and I'll stop here. There we go. So you can see it took 262 data points to pass to neural network and did better. There's 3 types of training: supervised, unsupervised, and reinforced. With supervised training, I have the data and I know the result, and I give it to the machine. And the machine has to figure out what to do with the data to get to the result. So if I give 2 and 2 equals 4, 3 and 3 equals 6, the machine will figure out that it has to add 2 and 2 and 3 and 3. With unsupervised, however, we don't know the result. It happens sometimes when we collect the data and we don't know what the result is. So we give as much more as possible data to the machine, and machine will learn from experience what to do with the data. Reinforced type is more new and more progressive. This type of training is when the machine doesn't have the data, it learns from its own mistakes. For example, self-driving cars. The machine will get either reward or a penalty. And with self-driving cars, there's no simulation how we can train our cars what to do in certain situations on the road. So the car will figure out on its own in real time what to do in case something happens. Under supervised training, we have 2 types of datasets: training and testing. Both of these datasets have data and expected result. But training data has much more data in it than testing. With training data, we technically teach our model what to do with the data. And with testing dataset, we just test how correctly we trained our model. So when we're in testing phase, our model will tell us how closely it predicted the result. So for our workshop, we'll have images of handwritten digits that were broken down into pixels, and they were fed to CSV format, which is the most organized type of data. So supervised training has 4 steps. First, we'll build a model, then we'll train it, then we'll test it, and then last step we'll evaluate it. So next we'll take a look at the code. So as you open Anaconda Navigator, go to Environments, and under Packages Not Installed, you'll search Keras. But the one I want you to install is the regular one. It will call Keras Deep Learning Library for Theano. And the way you install it is just like you will select and you'll hit apply. Mine is already installed, and it should take a couple minutes to install. Once it's installed, go to Jupyter and you'll launch it. So this is my Jupyter. Now we'll have to unzip the file that you downloaded. So I'm gonna unzip it. Okay, now I'll go back to Jupyter and I'll go to the file where I saved it. There we go. And I'll open It's called Deep Neural Network Carseway APY and B. So here's our file with code, and our first step will be importing all required libraries. And as you can see, the code is here. So in Python, when we want to import a library from Python, we will just use import function. We'll send the name. And when we say as, that's just we assign a new name or a variable to the library. However we want, however conveniently for us will be to call it later. So it will be just np. So we'll import numpy, which provides support for more efficient numerical computation. And then we'll import pandas, which a convenient library that makes it easy to load, read, and manage the data. Also, we'll import matplotlib.pyplot as plt, and that library will help us to build plots. All of this library is essential for building our model, neural network model. And here it's just a library that will print us in case we'll get an error, and it will print it for us. We will not, but just to be precautious, especially when you're building a model, you want to include that. So let's run that. And you should see a message. There we go. And this is normal. It will not cause any issues. Scroll down. So you can see there's a couple missing codes that we'll be filling out. The first missing code is we need to import our training and test data. Delete that. So I'm gonna create a train variable, and in Python we do not define, like we don't use var or anything. We just say what we want. So much easier. Next, I will use pandas library pd, and as you remember, pandas, I created my own name for pandas library. And when we're using libraries functions, we have to specify where this function belongs. So I'm using pd library, and I will use read csv, open parentheses, and the file will be called train.csv. Next line, I'll have to print print open parentheses, and then I will print how my data looks like. So I'll get train variable dot shape. This is a function, and it will show me the shape of my trained data. And we can print it out. Dot head. Okay, let's run that. So as you can see, we imported trained CSV, and we printed out that we have 2010 rows and 785 columns. There should be 784 columns plus 1 for labels. We have 28 by 28 pixels pictures, and when we multiply 28 by 28, we get 784, one row of data for our image. And I just printed out the first 5 rows of data. We're also missing some code for our test data. So I will create test variable, call pandas read CSV. And if you're lazy, you can just copy that code and paste it. But just change, instead of train, to test.csv. We'll also print it, test.shape, and then test.head. All right, and I'll run that. With test, we have much larger data. We have 28,000 rows and 784 columns. Here you have already data, and the data we feed in our model is already pre-processed for our model. But to have peace of mind, we will set the values float32 type, and it just makes sure that image is in 1D format. And when I'm saying in 1D format, it means just like in one row, having 784 pixels. So the whole image is just a one row array. And the array is from 0 to 255 number. Let me try to open our file. So here's our file, and as you can see, the whole picture, black and white picture, the person who wrote it down, the number, and then transformed the picture to pixels and then transformed it to numeric. It's a whole process, but now this picture is in numeric value from 0 to 255, and I already moved it. It used to be in one single array, but I started like whatever it was after 28, I moved it to the new line, and then whatever was after 28, I moved it to new line. So this is number 3, and this is just whatever was number 0, I put it in white, and whatever is above 0, I put it in black color. So as you can see, this is number 3. Let's go back to our file. So this just code is making sure that a file is ready to go. We'll run that, And as you can see, this is an array. It's showing me that this is an array. Okay, let's go to data visualization. We have code here too. So now we will create a new variable, a new name, and then for xtrain, which we created before, xtrain, we will reshape the array, this whole line, and we'll reshape it. We'll take the first number, we'll reshape it to 28 by 28, just like I did manually. And just in certain range, we will print out how it looks like. So if I run that, so our zeros, this is our zeros, and it's just showing us how data looks like. And then in here, we'll just add one more attribute, channel gray. So channel gray just minimizes the picture. Usually our pictures have like about more than one channel, sometimes like 3 channels. Just one channel will make it so much easier for our model to process the image, and it will not take a lot of computer power when we're doing so. And it gave us output that it has 2010 rows, 28 by 28 pixel, and this is a gray channel. And let's do the same thing for test. So now we have additional code available. So we'll have to standardize our data to feed it into our function. If you remember those terrible graphs, they are from 0 or -1 to 1. So we'll take these numbers, whatever was it, 255, and we will put them down to the value from 0 or -1 to 1. And this is done by our favorite statistics, z-score, where mean is equal to 0. So we first calculate the mean of our training data, and we also assign it to be one-dimensional format, and we calculate standard deviation. And after that, we run a function, standardize, that will bring our data from 255 or 178 to range from -1 to 1. So next step, we'll create categories for our numbers from 0 to 9, and we'll have 10 categories for that. So we'll import the library and we'll import two categorical function. We'll call yTrain a variable which has yTrain dataset, and then we'll use function toCategorical to which we assign the number of categories that we need. And yTrain dataset has only 10 variables. So in number of classes variable that we create, we'll assign inside yTrain the shape of it and the shape of index 1, and that will only be 10. So we'll run that and we'll call num classes again, and which is 10. And in our next step, we'll just plot whatever's in index 9, or we'll plot, in other words, 10th label. And in Access, we'll just print out the range from 0 to 9. And I'll run that. As you can see in our 10th label, we have value 0. So for our next step, we'll just set a specific value when a function will be creating a randomized number. That's just, we'll make sure that when I'm sharing the file, you will not get a different output. So let's just dive in finally in neural network. So we'll import all of these functions again. Okay. And here we'll create our model. So first I'll create a new variable called model. And to it I'll assign a type of model, which will be a sequential. And this is a very base of our neural network model, which allows us to add more stuff to it. And more stuff that we'll be adding are layers. So to add layers, I'll call model.add. The first layer will be lambda. And lambda is good at performing basic arithmetic operations, and it also will be a stop point for our input data in case this is completely different type of data that we're seeking. So we're looking at standardized data, and then for input shape, we're really nitpicking. We need 28 by 28 pixels in grayscale. All of this been done in previous steps. We'll add one more layer, and this time we'll go backwards. It's called flatten. Oh, didn't mean that. Okay. And flatten layer will convert 28 by 28 pixels to single one-dimensional 784 pixel array. So we went way backwards. And for our last one, we'll use model.add. We'll use dense. And dense is a fully connected layer, which means that neurons can send their data to the next neuron, and next neuron can send their data to the next ones, and next neuron can actually retrieve the data from previous ones, just like we saw in neural network. And there's a couple things that we need to specify. First, we have to specify that for the last output, we only need 10 digits. And for our activation, we'll use softmax. And this is an activator that will be responsible for taking all the digits that came from flatten and lambda and throwing them into categories. So if it's number 1, it will throw in the category 1. And I'll print couple things. So input shape model. So I'll call model variable, and then I'll just print out what input shape was. I'll copy that. Very lazy. From input, I'll change to output. And then here, output as well. And let's run that. It said, sorry, name standardized is not defined, but it was defined. Right here. Standardized. Typo. We love typos. There we go. Let me run that again. There we go. So input shape means none. It accepted all of the data from our data. So we were not specific from which range we want to accept. We just accepted all of it. And it was 28 by 28 pixels. But we sent out all of the data that we knew, and we just sent out 10 numbers. Next, we'll have to compile it. And inside of it, we need to write one more code, which is model. We'll call model variable, and we'll assign to it a function, which is called compile. And inside of it, we need to tell a couple things, which is optimizer one of those equals RMS prop. We'll use RMS prop because it is more suitable for our model. It allows take the output from previous layer to be the input for the next one. And we'll assign to it learning rate, which is 0.01, the default. Next, I will tell about loss, and it will be categorical. Cross entropy. Categorical cross entropy loss type is smarter than common mean square error and works better in logical models, which we are currently using. And then comma, and one last thing is metrics. Equals squared brackets, quotation, accuracy. And since we're doing classification problem, we want to set the metric to accuracy. And we will run that. Awesome. For the next one, it's just will take care of us for the images. We'll just run that. For now, our next step in cross-validation, we'll just use scikit-learn to split up our trained data. Usually trained data is huge. The original one has 42,000 rows, and if I had 42,000 rows, I would need to split it up in a couple more variables, or just like split it up in 2 variables instead of having 1. I'll need to add 1 more code. And our last step will be actually training our model. So I'll create history variable, which will contain all of the output our training function is sending out. And I'll call model variable, and I'll feed that into fit generator function. And there's a couple things that I'll have to specify to train our model, which is generator equals batches, which is 64. And batches is how many training examples we're using at each step, and each step is defined by epochs. And epochs tell us the number of times entire training data is passed to the neural network for training. So I'll continue steps per epoch equals batches dot n, which is number of batches, and epochs equals 3, comma, I'll continue validation data. That's actually our data. Equals val batches, comma, and validation steps equals val batches dot n. So let me run that. And it will take a minute, I would say, to train itself, and it has 3 steps. So while it's training, I'll just continue writing the code. So I'll move down. All right. So in this step, we will create a fully connected model, and it is similar to the one that we created before, but the only difference will be is that it will be fed under a function. So let's do that. So I'll define get fully connected model and a colon. So in Python, when we create a function, we don't do curly braces. We actually, when I hit return or enter, it will put me in a new line and a little bit indented inside under function. So when Python reads the code, it understands that this line of code, it belongs to the function. So I'll create a new variable called model, and same thing, sequential. And the only difference here will be squared brackets. And inside here, I'll be adding new layers. But instead of using a function model.add, I'll just be calling them. So I'll be doing lambda, and it will take standardized data and an input shape. Be 28 by 28 pixels and grayscale, comma, we'll flatten it. We'll add one more new layer that we didn't do before. It will be dense, but we'll send out 512 pixels, and activation will be ReLU. And that has to be under quotation marks. Here we go. And a final layer will be also dense, but the output will be 10 digits, and activation will be softmax. Okay, after that, we will need to compile that. So model.compile, add a few more things. Optimizer equals Atom. And for loss equals categorical entropy. Okay, I'll stop here for a second if you're typing. And matrix equals square brackets accuracy. And last thing is that we'll have to return something when we run a function. So we'll return a model. This is it, and I'll run that. Now, we have to train this model, but we have to first do something different. So first I'll create a new variable called fully connected, shortly FC, and I'll feed to that variable the function get C model. Instead of writing a long right here, writing very long, I'll just feed the function under variable. And then I'll set an optimizer to that. Optimizer learning. I'll set up learning rate, not the optimizer. 0.01. And I'll run that. I know what happened. Standardize. And typo. Run that. Oh boy. I know what happened. Forgot equal. There we go. And now we'll start training it. Oh boy. Come on. What happened? Argument metric, pass k function, package. I think it's metrics. Oh man, typos. There we go. Alright. And I haven't forgot about the previous one. It has to be completed, and as you can see, as every time we'll run the whole dataset through the model, the accuracy improves and our model improves as well. So now this one should take a minute to finish, and it's also, as you can see, it's improving itself. Okay, evaluation. That means it's the last step. All right, I'll just wait till it's done. So for our last step, we'll have to train our model one more time, but this will be a last time to make sure that our model is fully trained. And then we'll pass it on to predict function, to which we'll pass our test dataset. So we'll do model optimizer. Learning rate equals 0.01, and then gen equals image data generator. And then batches equals gen flow x, y. And then last, we'll just train it. Let me just copy that. Go up, and I'll just copy that. And I'll run that. Oh boy. Oh, it has to be a small one. There we go. So it's useful, it usually tells you what is wrong. And our accuracy is skyrocketing. Wow. Okay. And very last code is prediction. Equals model dot predict classes, and then x test, and then verbose equals 0. And verbose usually means that we usually set it to above 0 if we need additional information about it, but in this case we don't need our function to send an output in more detail. And I'll just wait for it to finish. Wow, accuracy is like 1, like 100%. Okay, it's done, and then I'll run that. And it should send out to the folder which this file is located, dr.csv. And in there you'll see its CSV file with its predictions and what it thinks it is. So this is the file it's submitted. So we have image ID, and as the function image, it was taking care of images, and our model actually predicted that under image ID 1, the number was number 2, ID number 2, the label was the number was 0. So this was TD Workshop 3. And I hope you guys enjoyed it. I hope you learned a lot. I know this topic is very complex, and I tried to explain it as very plain as possible. And I am confident that in case you are actually get interested in this topic, you will be able to learn more, to add more stuff to it. And honestly, if a Terminator error comes in and we'll have machines, we'll have to fight against them. I mean, you can be confident that you can hack them and you can make a typo like I did, and it will mess up the whole thing. You can be sure of that. Alright guys, this is all, and I'll see you at TD Workshop 3.